When you set up a mass on a spring, you extend the spring to a new equilibrium position where the forces acting on the spring are equal. The amount the mass extends the spring is determined by the properties of the spring, such as density of the metal and thickness of the wire. All these properties can be summarized using a concept introduced in the AS Physics topic, Bulk Properties of Materials podcasts. The concept is Hooke's constant. This value tells us how springy the spring is. The position of the equilibrium is also determined by the magnitude of the mass being added to the spring. The bigger the mass, the greater the extension of the spring. All this is summarized in Hooke's law, stating that the restitutional force is equal to Hooke's constant K multiplied by the displacement x multiplied by -1 to show it is a restoring force. From Newton's second law, we know that force is equal to mass m times acceleration a. Hooke's law and Newton's second law are both true, so we know that force equals -kx, and it also equals ma. That means that ma equals -kx. If you rearrange this, you can show that acceleration in the spring is equal to -kx divided by m. From our studies of simple harmonic motion, we know that acceleration is equal to -2 pi f squared times by displacement x. Acceleration in a simple harmonic oscillator is the same as linear acceleration and obeys Newton's laws, so we can say that the acceleration in Newton's law, which we've shown is equal to -kx over m, is also equal to the acceleration in simple harmonic motion, -2 pi f squared x. Putting these two equations together, we can see the displacement term is cancelled out, and so are the negative terms. K divided by m is equal to 2 pi f squared. We could rearrange this equation to give us an equation for frequency in terms of physically measurable quantities, mass on the spring and Hooke's constant. However, it is difficult to measure frequency. It is much easier to measure the time period of the oscillation. Frequency equals 1 divided by time period. This means our equation now becomes K divided by m is equal to 4 pi squared divided by t squared. We also square the 2 pi and f at the same time to get 4 pi squared and t squared. We rearrange the equation and cancel terms to give us an equation for the time period of an oscillating mass on a spring as t equals 2 pi times the square root of mass divided by Hooke's constant. You can do something similar when you look at a pendulum on a string oscillating under simple harmonic motion. Here, instead of using Hooke's law for springs, we look at acceleration of objects due to gravity. An object will accelerate in a gravitational field depending on the mass of the object and a local gravitational field strength, g. F equals mg is also equal to ma. This means the acceleration is the same as gravitational field strength. So instead of a, acceleration equaling -2 pi f squared x, we have g equals -2 pi f squared x. Instead of using the general acceleration equation involving a negative term, we'll use the maximum acceleration term and remove that negative. This means that the gravitational field strength g is equal to 2 pi f squared times the displacement. We rearrange the equation to give g divided by x equal to 2 pi f squared. As above, f equals 1 over the time period, so our equation becomes g divided by x equals 4 pi squared divided by t squared. You move the t across and the g and x across to make the time period squared equal to 4 pi squared x over g. Remove the squared by square rooting to give a time period of oscillation equal to 2 pi times by the square root of x over g. As we've used the maximum acceleration equation, we know that maximum acceleration happens at maximum displacement. This happens when the displacement equals the length of the string, so instead of using x for displacement, we now use L for length of string. The time period of a pendulum is equal to 2 pi times the square root of L over g.